Okay, today I'd like to talk to you about some of the things we learned about circuits last year. I want to start with batteries, and I want to remind you that batteries are a device where chemical reactions are able to produce electrical energy. So in this case, we have zinc and copper placed in some sort of acid. We have the zinc turning from zinc metal into zinc ions, which will be entering into the solution. They leave behind electrons, which are going to make the zinc have a negative charge. At the same time, on the copper, we're going to have the hydrogen ions from the acid stealing a few electrons from the copper to produce hydrogen gas. That is going to leave the copper positively charged. What we're then going to see happen is a voltage or energy difference exists between the two metals. The voltage will be the change in energy per charge between those two metals. The voltage is going to be determined by the type of chemicals and the concentration of the chemicals inside the battery. Once we have a negative and a positive with an energy differential, we can have the electrons repel each other through an object such as a light bulb and transfer some of their energy into the bulb. Okay, so that is your basic battery information. I want to remind you that D batteries are 1.5 volts, C batteries are 1.5 volts, AA and AAA are all 1.5 volts. This reminds us that the volume of the battery does not affect the voltage. The volume just helps to determine how much chemical is present, which will determine how long the battery is going to be able to last. Okay? The actual voltage is not determined by the size of the battery, but by the type of chemical reactions taking place. I want to remind you that we can combine batteries together to get higher voltages or longer life. For this first one, we would say that these batteries are connected in series. We have our negative of battery 1 and our positive of battery 1. You then want to hook the positive of battery 1 to the negative of battery 2. And then you continue this process, positive to negative, positive to negative. You see these metal strips are connecting the positive to the negative. Then the final positive is where you want to have your connection. You have one connection at the original negative and one connection at the original positive. Each of these batteries is 1.5 volts for a combined voltage of 6 volts. In parallel, which is our second type of connection, all the positives are connected together and all the negatives are connected together. The positive can come off of any of the batteries, and the negative can come off of any of the batteries. This will give us 1.5 volts, which is the same voltage of each individual battery. So what's the point if we're not increasing the voltage? We are increasing the lifetime for that these batteries would last. Okay, we have a resistor, and we'd like to hook up these batteries in series to this resistor. So we would take our negative and hook it to positive. We'd take our negative and hook it to positive, our negative and hook it to positive. Then we'd take the one positive that is not connected to anything else and connect it to the resistor. We would connect the negative on the other end that is not connected to anything else to the resistor. This would give us 8 volts based on the way we connected these. Again, it is a series connection and it leads to higher voltage. If we want to connect in parallel, we connect positive to positive and negative to negative. Then we connect either of the positives and either of the negatives to the resistor. It doesn't matter which one you hook up. This would give you 2 volts, but it would last twice as long as a single battery. Okay, I want to remind you of the important terms. Voltage, which we've already talked about. Voltage is the difference in energy per coulomb. It'll be measured in joules per coulomb. It tells us how much energy we'd get for each coulomb of charge that passes through our system. Current, on the other hand, goes by the letter I, and that is the amount of charge that passes through an area per second. It can be measured in amps, which means coulombs per second. Interestingly, if we multiply the current, which is charge per second, by the voltage, which is energy per charge, the charges cancel and we get joules per second, which is power. So power equals voltage times current. We have a fourth term called resistance, which was developed back in the 1800s by George Simon Ohm. He labels the resistance in a unit called ohms, and what ohms represents is how much voltage it would take to push 1 amp through an object. So if an object had, let's say, 15 ohms worth of resistance, that would mean it would take a 15-volt battery to make 1 amp flow through that object. We now know that the resistance of something like a wire depends on 3 different factors about the wire. One is the material. It's called the resistivity of the material, and it goes by the letter rho, the same letter we use for density. You could see on your reference sheet the rho values of different things. You could see silver has the lowest. The lowest resistivity means it's going to be the best conductor. Graphite, you'll see, has the highest number. That's going to be the worst conductor from the things on this list. So we have type of material is one factor. We have length as another factor. Longer wires have more resistance. It's going to be harder to push the electricity through a longer distance than it would be a shorter distance. Finally, the thickness of the wire. It's easier if the wire is thicker. So all of these factors came together, and the formula for the resistance of the wire looked like this. Material, length in meters, area. The area is if you took a slice of the wire and you looked at that circle, that cross-sectional circle, found the area of that circle in meters squared and plugged it in. There's also devices known as resistors. I hope you remember how to read it. Here are the color codes. Remember, it starts at 0, and then each color represents a different number. And these colors work for bands 1, 2, and 3. So if we have red on band 1, that's a 2. If we have green, that's a 5. For the third band, you still use these colors, but it tells you the number of zeros. So orange tells us to add 3 zeros. Here we have yellow, that's a 4. Purple, that's a 7. And red is 2 zeros. The fourth band tells us like the tolerance of the resistor, how close it's going to be to what we just figured out. Gold represents an error of up to 5%, and silver represents an error up to 10%. They also help us orient the resistor. So if we see, for instance, a silver band, we know this is band 1, 2, and 3. If the silver's on this side, then we start with this brown one as 1 and 2 and 3. So not only does it tell us the percent error, the possible percent error, but it also helps us figure out which end of the resistor to start reading from. I want to remind you of Ohm's Law, which relates our three variables together. It says the current that is coming out of the batteries and flowing through our circuit is equal to the voltage of the batteries divided by the resistance of the light bulb. So if we have more voltage, we get more current. If we have more resistance, we get less current. So when we're trying to figure out what's going to happen with our light bulb, we need to know the voltage, we need to know the resistance. We can then calculate the current. Once we have the current, we could find the power by doing current times voltage. We could then take the power and find out how much energy we're going to get from our battery in a certain amount of time. So these are the four big terms that we have for electricity. Voltage from the chemicals in the battery, resistance from the object that we're powering, current, which depends on voltage and resistance, and finally power, which depends on the voltage and the current. So hopefully you remember most of these terms, and hopefully you'll be able to use them.